Hello everyone. In order to describe the phenomena of motion and change in the real world, mathematics introduced the concept of function. Function is an important concept in mathematics. With in-depth research on functions, mathematicians created calculus. This is a great creation with epoch-making significance and is hailed as a milestone in the history of mathematics. The establishment of calculus is directly related to dealing with four types of problems. First, it involves the problem of object motion. Given the distance traveled by an object as a function of time, the goal is to determine the object's velocity and acceleration at any given moment. Conversely, given the acceleration of an object as a function of time, the goal is to determine the velocity and distance traveled. Second, it involves finding the tangent of a curve. Third, it involves finding the maximum and minimum values of a function. Fourth, it involves solving problems such as finding length, area, volume, and center of gravity. Historically, scientists have shown enduring interest in and conducted extensive research on these issues. Finally, in the mid-17th century, two great mathematicians, Newton and Leibniz, based on the exploration and research of their predecessors, independently established calculus with their keen intuition and rich imagination. The derivative, which we will study today, is one of the core contents of calculus and a fundamental concept in modern mathematics, embodying the basic ideas of calculus. The derivative quantitatively characterizes the local changes of a function and serves as a basic method for studying properties such as the rate of increase or decrease, maximum and minimum of a function. Therefore, it is also a fundamental tool for solving practical problems such as growth rate, expansion rate, efficiency, density, speed, acceleration, and so on. Today, we will explore a type of rate of change problem closely related to the derivation. We have previously studied the monotonicity of functions and know that different types of functions increase or decrease at different speeds. Can we accurately quantify the speed of change? Today, we will take the speed of high-diving athletes as an example to study. In high diving, the height h of an athlete's center of gravity relative to the water surface, measured in meters, is a function of the time t since takeoff, measured in seconds. Specifically, ht equals minus 4.9 times t squared plus 4.8 times t plus 11. So, how should we describe the speed of the athlete's movement from takeoff to entry into the water? We know that during the process from takeoff to entry into the water, athletes will move slower and slower during the ascent phase and faster during the descent phase. The speed of athletes is changing all the time. To study the changes in an athlete's speed, we can divide the entire period of movement into many small segments and use the average speed of the athlete during each segment to approximately describe his movement state. How should we calculate the average speed of an athlete during the two periods, from the takeoff to 0.5 seconds, and from 1 second to 2 seconds after the takeoff? We need to calculate the function values corresponding to the end times of the two time periods, which are 0.5 seconds and 2 seconds, as well as the initial times, which are 0 seconds and 1 second. Then, we calculate the difference between them to obtain the change in the athlete's height above the water surface during the two time periods. Finally, we divide this difference by the change in time during the two time periods, which is the difference between the end time and the initial time. This will give us the average speed of the athlete during the two time periods. Represented in symbolic language, the average speed during the first period is equal to h0.5 minus h0 divided by 0.5 minus 0, and the average speed during the second period is equal to h2 minus h1 divided by 2 minus 1. After studying the calculation method of average speed, we can entrust the specific calculation work to information technology tools. You can take out your calculator or computer and calculate the values of the two equations just now. So we have obtained the average speed of the athletes during the two periods just now, where the average speed is positive. This indicates that the height of the athletes relative to the water surface has increased during this period, while the average speed is negative. This indicates that the height of the athletes relative to the water surface has decreased during this period. So how do we calculate the average speed of athletes from t1 seconds to t2 seconds after takeoff? According to the analysis just now, the time period should be t1 less than or equal to t less than or equal to t2. We subtract the function value corresponding to the initial time t1 from the function value corresponding to the termination time t2, and then divide by the value of t2 minus t1 to obtain the average velocity during this period. Expressed in symbolic language, the average speed during this period is equal to ht2 minus ht1 and then divided by t2 minus t1. After we know the method for calculating the average speed of any time period, please calculate the average speed of athletes during the time period when 0 is less than or equal to and t is less than or equal to 48/49 seconds, and see if you have any findings. After obtaining the expression for the average speed of any time period, we can first write the expression for the average speed of this time period. Everyone can first use a calculator to calculate the result themselves. We calculated that the average speed of the athletes during this period was 0. So, what do you think would be the problem of using the average speed of this period to approximate the athlete's movement state during this time? In fact, during this period, the average speed of athletes is 0. But obviously, except for the moment at the highest point, athletes are always in motion, and their speed is not 0 at every moment. The average speed of athletes only focuses on the period from the beginning to the end, ignoring the intermediate movement process, so it cannot accurately depict the athlete's movement state. To describe the athlete's state at each moment, we need to study instantaneous velocity. What is the relationship between instantaneous speed and average speed? Can you use this relationship to calculate the instantaneous speed of an athlete when t equals 1 second? Let's first examine the relationship between instantaneous velocity and average velocity. Assuming that the average speed of the athlete during a certain time period near t0 is v bar, it can be imagined that if the length of this time period is continuously shortened, the average speed will gradually approach the instantaneous speed of the athlete at t0. Following this idea, we want to calculate the instantaneous speed of an athlete when t equals 1 second. Then we take any time after or before t equals 1, where 1 plus delta t. Delta t is the change in time, so it cannot be 0, but it can be positive or negative. When delta t is greater than 0, 1 delta t is after 1. So we can calculate that the average speed during the time period 1 to 1 plus delta t should be equal to h1 plus delta t minus h1 plus 1 plus delta t minus 1. Substituting the expression of ht for simplification and organization, obtain the delta t divided by negative for 0.9 times, then subtract 5 times the delta t. Finally, simplify to the following result, subtract 5 from the delta t divided by negative for 0.9 times. If delta t is less than 0, then 1 plus delta t should be before 1. During the corresponding period, we also carried out similar processing. In the end, the simplified expression for the average velocity during this period is still negative 4.9 times delta t minus 5. So, we obtain the following table. It can be seen that regardless of whether delta t is greater than 0 or less than 0, the average velocity expression during this period is negative 4.9 times delta t minus 5. Next, we will have delta t continuously decrease the value of the observed average speed. We can use an Excel spreadsheet to see the changes in the average speed v as the time interval decreases. When delta t is greater than 0, we take 1 as the initial value, and then take 1/10 of the previous value each time as the new delta t value to see the change in average velocity. It can be seen that as delta t decreases, the average speed value will gradually approach negative 5. When delta t is less than 0, we also perform a similar operation. It can be seen that as the time period continues to shrink, the average speed value also tends to approach negative 5. It can be seen that when delta t approaches 0 infinitely, regardless of whether t approaches 1 infinitely from the side less than 1 or the side greater than 1, the average velocity will infinitely approach negative 5. Is this a coincidence or an inevitable outcome? We can try to provide more values for delta t and use information technology tools to calculate more values for average velocity. Let's observe the trend of the average velocity when delta t approaches 0 infinitely. For example, we can take some other values from the table just now to verify. Enter any number as the initial value for delta t, then take 1/7 of each value as the new delta t value. As can be seen, the same result was obtained. The average speed will approach negative 5 meters per second. You can also use this table to take more numbers for verification after class. It can be seen that regardless of the positive or negative value of delta t, as long as it approaches 0 infinitely, that is, the time interval keeps decreasing, the average velocity will infinitely approach negative 5. Does that mean that when t waits for 1 second, the athlete's instantaneous speed is negative 5 meters per second? Do you think the process of calculating instantaneous velocity through a list is reliable? In fact, by calculating the average velocity value earlier, although we found that as the time interval decreases, the average velocity becomes closer to the constant -5. However, calculations are limited and cannot determine whether the average speed will always have this characteristic. We need to explain it from a more rational perspective. We can further organize the process just now, based on the expression of h1 and the time period we have taken. A unified expression for the average speed during this time period was obtained, and the -4.9 times delta t was further reduced by 5. We observe the equation of delta t minus 5, which is -4.9 times. When delta t approaches 0 infinitely, it is obvious that a -4.9 times delta t will also approach 0 infinitely, so the average velocity naturally approaches -5 infinitely. We call -5 when delta t approaches 0 infinitely. The limit of delta t divided by h1 plus delta t minus h1 is expressed as follows. Among them, lim represents the operation of finding the limit of this equation. Delta t approaching 0 represents the condition for finding the limit. We explain the conclusion we just obtained through calculation from a more rational perspective. So, can you use the above method to calculate the instantaneous velocity when t equals 2 seconds? We can still use a similar method as before, taking the time interval as delta t. Therefore, the average speed of the athlete in the time period after or before 2 seconds is h2 plus delta t minus h2 minus delta t. Substituting into the expression of ht, we simplify and organize it to obtain a delta t minus 14.8, which is -4.9 times. Obviously, when delta t approaches 0, the value of this equation will approach -14.8. So the limit of this equation when delta t approaches 0 is negative at 14.8. That is to say, the instantaneous speed of the athlete at t equals 2 seconds is -14.8 meters per second. After calculating the instantaneous velocity at 2 specific times, can you derive the expression for the instantaneous velocity at any time t0? Let's still compare the process just now and get the following general result. Take the time interval as delta t, and during the period after or before t0, the average speed of the athlete is ht0 plus delta t minus ht0, then compared to delta t. Substituting the expression of ht for simplification, the following result is obtained: -4.9 times delta t minus 9.8 times t0 plus 4.8. When delta t approaches 0, the limit of this equation will approach -9.8 times t0 plus 4.8. So we obtained that the athlete's instantaneous speed at t0 is -9.8 times t0 plus 4.8. We have completed the study on the instantaneous speed of athletes. To know the instantaneous speed of an athlete at any given moment, simply input the corresponding moment into this equation for calculation. Looking back at the process just now, we obtained the instantaneous velocity by continuously narrowing the time interval and approximating it with the average velocity. Instantaneous velocity is the limit of the average velocity when the time interval approaches 0 infinitely. The idea of infinite approximation is also the foundation of calculus. What have you learned from reviewing the exploration process of this lesson? From a knowledge perspective, we mainly studied the movement state of high platform divers after takeoff. We first studied the average speed of athletes during a certain period of time after takeoff and continuously narrowed down the time interval. As delta t approaches 0, we obtained the instantaneous velocity of the athlete using both computational and limit methods, and derived the expression for the instantaneous velocity at any time t0. Through this process, we realized that instantaneous velocity is the limit of the average velocity when the time interval approaches 0. From the perspective of research methods, we used the infinite approximation method to obtain the instantaneous velocity through the average velocity, which contains the idea of limits. The limit idea of infinite approximation is an important method and foundation in derivative research. We have derived the expression for the instantaneous velocity at any time t0 by extending it to specific moments. This approach, from special to general, is also a commonly used method in mathematical research. We hope that everyone will continue to experience its application in the study of derivatives in the future. That's all for this lesson. Goodbye, everyone.